Okay, thank you everyone for attending my talk. My name is Pratish Mahtani. I'm a PhD candidate in Professor Nazir Karni's group at the University of Toronto. I'm going to begin my talk by discussing the motivation for my research, and like many of us in this room, my motivation is to help contribute in developing the next generation of solar PV technologies. I will point towards the amorphous crystalline silicon heterostructure solar cell as a candidate design for a next generation solar cell. I'll describe the novel grid-based plasma processing, which is the contribution that I've made to the silicon heterojunction solar cell field, and describe some of the promising results that we've achieved thus far. So it's pretty clear that there is a significant energy and climate change crisis that we're facing globally. And it is also clear that solar PV is going to play a major role in tackling these challenges. In fact, it's been projected that over the next 40 years, solar PV will move from about 0.1% of the global energy production to about 6%. So that's a huge increase over a relatively short period of time. The question is, how are we going to bridge that gap? What technologies are we going to use to be able to go from 0.1% to 6%? And we've discussed in a lot of the talks in this conference about different candidate next generation technologies. We've heard about organics and nanostructures and 3-5 semiconductors, and these are all really promising technologies that will play a significant role in bridging that gap. But we must not also forget that crystalline silicon is still the mainstay in the solar cell industry. It's 88% of the market share, and there's very good reason for that. It's abundant, it's non-toxic, and it's stable under light. It's also, with the falling cost, relatively cheap as well. We also must not forget that silicon PV is not a static industry. It's not a static research field. There have been significant breakthroughs over the past few years that have completely changed the landscape in the silicon PV research field. One of these game-changing breakthroughs was the advent of the silicon heterojunction solar cell. So to understand the silicon heterojunction solar cell, I'll first describe the conventional textbook silicon homojunction solar cell. So we're all pretty familiar with this. And usually you fabricate these cells, you start with a P-type crystalline silicon wafer. And then through thermal diffusion, you go through a very high temperature, about 1,000 degrees Celsius thermal diffusion process. You can introduce impurities into the crystalline silicon lattice to form rectifying and back surface field junctions in the cell. And then you add on your anti-reflective coating and your front and back metallization, and you have your complete cell. Now, the silicon heterojunction solar cell, you start off very much in the same way. You can use a P-type or an N-type wafer. N-type tends to be a little bit more commonly used, but either would work. But this is the main difference. Instead of using the high temperature thermal diffusion process to form the necessary rectifying and back surface field junctions, use a very low temperature process. Use a 200 degrees Celsius PECVD process to deposit a different material. And this different material is hydrogenated amorphous silicon material onto the crystalline silicon wafer, on both sides of the crystalline silicon wafer, to form the rectifying and back surface field junctions. And then, much like the homojunction, you add a transparent conductive oxide, which also acts as an anti-reflective coating, and then your front and back metallization, and you have your complete cell. So there are a number of advantages of the silicon heterojunction in comparison to the homojunction design. The two main advantages are, one, you have low temperature processing. So all the processing to fabricate the cell is done below 200 degrees Celsius. And as Kevin had described earlier in this session, that with using low temperatures, you can apply this to ultra-thin crystalline silicon wafers, which has numerous advantages. Another major advantage of the silicon heterojunction solar cell is that it has excellent surface passivation. So the hydrogenated amorphous silicon, in addition to providing the rectifying and back surface field junctions, also passivates the crystalline silicon surface. And crystalline silicon, most of the defects lie on the surface. And so if you're able to passivate that surface, you can get really high efficiency solar cells. And this has been demonstrated recently. Actually, just a few months ago, Panasonic had released a report where they are showing 24.7% efficiency with the silicon heterojunction solar cell. So using this relatively simple fabrication process, you get state-of-the-art silicon PV efficiencies. There are a number of other advantages. You get improved temperature stability. So silicon solar cells, like many other solar cells, the efficiency decreases as you increase the operating temperature. The heterojunction solar cell is a little bit better. The decrease is a little less drastic. The payback period is lower because you have a more efficient solar cell, and also there's less thermal energy put into the fabrication of the heterojunction solar cell compared to the conventional solar cell. The energy payback period is lower. Same reason is the greenhouse gas emissions are lower. You have a more efficient solar cell, less energy during the production, and so there's less greenhouse gas emissions over the life cycle of a silicon heterojunction solar cell. In terms of drawbacks, there's relatively few drawbacks. The main one lies in the fact that it's a relatively new technology. The homojunction solar cell has been around for over 50 years. The technology is quite well known in terms of how to process these cells. Heterojunction solar cell is relatively new, and so it's not well known how to properly process these cells. There's only really a handful of groups that can do this very well. And the main reason for this is that the physics and dynamics of the hetero interface are not well understood. And the optimal method of depositing the amorphous silicon film to get really good hetero interface properties is not well known. So this is what really motivated my research, and this is where my research comes into play, is that we developed a fabrication tool specifically designed for really good silicon heterojunction properties. So the conventional way to deposit hydrogenated amorphous silicon is with a diode RF PECVD process. And it's a diode process because there's two electrodes. There's a RF powered cathode and a grounded anode. And typically your crystalline silicon wafer will lie on that grounded anode. And there's a plasma formed between the cathode and the anode, and your crystalline silicon wafer is exposed directly to this plasma. There's very little control over the energy or type of precursors that are involved in film growth using this conventional process. And also your substrate is exposed directly to the plasma. What we did is we applied a method known as the grid-biased triode RF PECVD process. And what this method is just a simple modification over the conventional diode PECVD. And the only major difference here is you're adding in a DC biased grid. And this DC biased grid confines the plasma between the grid and the powered cathode. So now your plasma region is separated from your growth region. Your crystalline silicon substrate is not exposed directly to your plasma. And by modulating the DC bias and also the distance between the grid and the substrate, you can control the energy and type of precursors that are involved in the silicon growth. This also it plays a major role in terms of getting good hetero interface properties, because now your precursors, you can modulate the energy of these so they don't damage the crystalline silicon surface, and also you can have the appropriate precursor species to get really good hetero interface properties. So to demonstrate the validity of this method in terms of getting really good, effective hetero interface properties, we performed an experiment where we deposited 30 nanometers of intrinsic hydrogenated amorphous silicon on both sides of a crystalline silicon wafer. And we used both the conventional diode RF PECVD method and the triode, which is with the grid configuration. We measured the surface passivation using a Syntin photoconductance instrument to measure the quality of the passivation. And we also were able to deduce the interface defect density through the surface recombination velocities that are measured. In addition to measuring the passivation quality, it was really important for us to also know what the bulk film quality was, because although the passivation quality is really important in the silicon heterojunction solar cell, so is the bulk amorphous silicon film properties, because the carriers that are generated in the crystalline silicon wafers still have to be transported through the hydrogenated amorphous silicon film. So it's really important to have films that aren't really defective, so you don't get a lot of recombination in the amorphous silicon layers. And we were able to measure the bulk film quality by looking at the hydrogen content and the microstructure parameter of the amorphous silicon films, where you lower hydrogen content and lower microstructure parameters point towards higher quality bulk properties. So what we found was, when we first took the grid out, so that's in the in the figure here showing 0 millimeter grid to substrate distance. That's without a grid. That's just a typical diode configuration. We got pretty good properties. We got a fairly low surface recombination velocity, and we got decent bulk film properties in terms of the hydrogen content and the microstructure parameter. Then when we added the grid in, we saw a slight improvement in both passivation and bulk film properties. And as we move the grid further and further away from the growth region, from the crystalline silicon substrate, both our passivation and bulk film properties increased dramatically. We actually were able to get state-of-the-art passivation below 3 centimeters per second, so about 2.5 centimeters per second in terms of a surface recombination velocity, and also very good bulk film properties. The question then arose is, could we achieve these same really good passivation and bulk film properties in the diode configuration by simply changing the RF power, changing the pressure to be able to control the energy or types of precursor species that are involved just using the diode configuration without the grid? And we found we couldn't. We couldn't achieve those same excellent properties that we had with the triode configuration with the diode configuration. So this is one example where we varied the RF power, and in the diode configuration, as you can see, as we changed the RF power from 5 watts to 25 watts, we didn't get very much change in terms of the surface recombination velocity. Actually, when we went down to 5 watts, we actually got even higher surface recombination velocity. So the passivation quality actually deteriorated a little bit. For the triode configuration, which is shown in the blue, we found that when we increased the RF power, we actually got even better passivation. It went even below 2.5 centimeters per second. So we got really excellent passivation properties. So it demonstrates the fact that the triode configuration really provides unique properties and effectively provides another parameter in terms of controlling the energy and types of precursors involved in amorphous silicon film growth. So just to summarize, silicon PV, and specifically the silicon heterojunction PV cell, will play a significant role in future global energy production. The grid-biased triode configuration demonstrates significant improvements over traditional diode RF PECVD, where we've demonstrated a 45% reduction in surface recombination velocity, a 43% reduction in the interface defect density, more than a 40% reduction in microstructure parameter, and more than 16% reduction in the hydrogen content. We also achieved state-of-the-art passivation. This is amongst the best reported in the literature for crystalline silicon solar cells, where I wrote here 6 milliseconds, but actually more recently we've achieved above 7 millisecond minority carrier lifetime in the crystalline silicon wafer, and below 2.5 centimeters per second in terms of the surface recombination velocity. We are now applying this method in fabricating full silicon heterojunction solar cells, and all the results we've achieved thus far really point towards really excellent results. So it'll be interesting to see once we complete those cells. So I'd like to thank you for your time and open up the floor to any questions.